Hello, welcome to Module 2 of the Grid 2 MOOC on multi-energy systems. And today we will be discussing about distributed lab middleware. I am Vetrivel, a researcher at the Department of Electrical Sustainable Energy at TU Delft in the Netherlands. So in the previous part of the MOOC, you were introduced to tools for multi-lab experiments. So in this part or the second module of the MOOC, we will look at the lab middleware, its software architecture, and some of the services that have been developed as part of it. The outline of this particular lecture is as follows. We will start by motivating the need for a particular middleware solution, followed by the software architecture of the middleware that we have developed within the Grid 2 project. Then we will look at some concepts such as research infrastructure as code and the universal API, which are crucial parts of the developed middleware solution. And finally, we'll draw some conclusions about what advantages the middleware offers and connect it to the last part of the MOOC. So the first question that we will seek to answer is, why do we need the middleware? And for that, we need to look at the challenges faced by the existing lab coupling solutions. And broadly speaking, the two biggest challenges are harmonization and interoperability, which means that these tools are typically cannot be used with each other as part of the same experiment, although they seek to achieve the same functionality in most cases, such as data exchange or giving a list of participating labs. So that's the biggest driver for developing this middleware. Furthermore, another key motivating factor is the ease of usage, to be able to use all these different tools in a much easier manner to carry out joint experiments. In the previous part of the MOOC, you have been introduced to some of these lab coupling tools shown here. So as we see, the first tool, Villas, provides a high data rate, provides connectivity, and can also be connected to physical equipment, whereas LabLink does not provide a high data rate, and Jander does not provide a high data rate and cannot be connected to physical lab equipment. So from this table, what we can summarize is that there is no one-size-fits-all solution when it comes to lab coupling. So different tools offer have different characteristics and therefore can be used for different applications. And there is a strong need for harmonization or to be able to make them interoperable with each other, which is the key focus of the distributed lab middleware. So what exactly would the lab middleware seek to achieve? The first aspect is focused on data exchange, for which the lab middleware was developed. And this is the most common functionality used in any multi-RI experiment. So the middleware would make it easier to be able to exchange data between participating labs in a joint experiment that are using different transport tools, for example. And therefore, it would improve the ease of access or usage for these multi-RI experiments. So this is the software architecture of how the middleware looks. And as you can see, it's divided into 4 layers, the lowest being the infrastructure layer, which is directly connected to the lab, a platform layer on top of it, followed by a software layer, and then an interface layer. In the previous module of the MOOC, we have already seen about the software layer and been introduced to some of those tools, such as Villas. So in this part of the MOOC, we will focus on the infrastructure and platform layers, and then also talk about the APIs, which are an important aspect of the entire middleware. So coming to the platform and the infrastructure layer, for this, we've developed something called as research infrastructure as code, which was inspired by the infrastructure as a code paradigm found in software engineering. And what this concept seeks to achieve is to be able to interconnect labs in a much quicker fashion and provide a high degree of automation for some of the most common tasks, such as setting up networks and VPNs, and to be able to log research data and, for example, monitor networks. So that's what research infrastructure as a code, or RIASC, does. And this is how the architecture of RIASC looks. So as you can see from the diagram, there are 3 different labs in this case, and each of them has a Kubernetes agent which enables them to communicate or talk with each other. And this is all managed through a central cloud which hosts the central Kubernetes orchestrator, which can orchestrate between these different labs. And these agents can be devices such as a Raspberry Pi, a dedicated PC, or a virtual machine. It doesn't really matter. It can be any kind of hardware platform. And that's how this RIAS concept was designed, to be able to make it possible for these agents to communicate with each other and for these labs to now then be part of a bigger network. And we utilize this infrastructure to be able to now interconnect labs, and we already have the tools to do so, as you have seen, such as Villas or LabLink. So then the key question is, how can we harmonize their functionality? And that's where the Universal API or UAPI comes in. And as the name suggests, the purpose of this API is to be able to standardize or harmonize some of the most common functionality used by these different lab coupling or transport tools. So it provides a layer on top of them to standardize some of their functionality. And this core functionality could include tasks such as data exchange, the list of signals that need to be exchanged during an experiment, the participating labs in an experiment, for example. And to keep it as widely usable as possible, the UAPI has been developed as a REST-based API, which is supported on a wide range of platforms and languages. And the best analogy to understand what the UAPI does is as shown in the figure of an example of ordering food at a restaurant, for example. In this case, the customer gives an order, and the waiter acts as the API, translating the request from the customer to the kitchen or the chef, who then responds back with the given order, which is translated again and delivered by the waiter, who is the API in this case, back to the customer. But we also have to keep in mind that the waiter does this for multiple customers at the same time, and that's what the Universal API seeks to do. So that customers in this case are different transport or lab coupling tools, and in the API translates some of their functionality. And this is the architecture of the API, of the UAPI. So as you can see on the figure on the left, there is a research infrastructure 1, and on the right, research infrastructure 2, which are involved in a joint experiment, let's say. And as you can see, in research infrastructure 1, the lab network is connected to the UAPI through something which we call as the RI adapter, which is nothing but a software which interfaces between the lab or the SCADA system and the UAPI itself. And the idea behind this is that this needs to be only developed once, such that in the future, if your lab needs to be interconnected or take part in a joint experiment, the UAPI can take care of all the abstraction, and you can use different transport tools for different applications with RI2. So essentially, through this kind of architecture, what the UAPI enables is that RI1 could be using lab coupling tool A, for example, while RI2 could be using lab coupling tool B, and they could still be used as part of the same experiment, which was not previously possible. So now let's take a look at how the UAPI is in action. So this is a screenshot of a terminal with different commands of the UAPI. So if we take a closer look, when we place an HTTP request, like for example a GET request, we see that from the remote to the local, so coming from, let's say, the other RI, from the previous example RI2, you get a list of the channels or the list of signals available that you can access or read. And what the UAPI also allows you to do is, of course, to write or send values back to the other participating RI in this experiment. So as you see on the next line, from the local to the remote, we write some values or send some values back to the other lab. And this way, the UAPI enables data exchange to take place. So, to wrap up this second module, what we have seen is the architecture of a lab middleware, which provides kind of harmonization or interoperability between these different lab coupling tools that you previously saw. And therefore, this middleware increases the usability for multi-research infrastructure experiments. And secondly, what this universal API provides is a simplification and standardization to some degree of the most common functionality used for these multi-research infrastructure experiments. And in the next part, we will focus on a case study utilizing some of these services that were covered in this module of the MOOC, focusing on a real-world, geographically distributed multi-research infrastructure experiment. Thanks for listening.